Hello, my name is Megan, and I'm a second year PhD student in the 3-5 Materials and Devices group. Today, I'm going to be giving a general talk on photonic integration methods. So this is an outline of what I will be going through today. So first of all, I will be talking about the importance of photonics and what is a photonic integrated circuit. Then I will be going through the pros and cons of using silicon in fabricating photonic integrated circuits. And then after that, I'll be going through the different ways of integrating devices with a photonic circuit and the advantages and disadvantages associated with them. So to start off this talk, the question should be asked, why is photonics important? Photonics is needed for many applications, but in terms of our everyday life, it's important for faster internet or data transfer. We live in an era where people are using streaming and social media services such as Netflix, YouTube, and TikTok, and many people and businesses are using cloud computing as an efficient way to store and access data. So there's an ever-increasing pressure to improve communication within and between data centers. If you look to the figure on the right, this shows the average internet traffic per month for the last 30 years. Petabyte, which is what the PB stands for, is 10 to 15 bytes of information. So by 2021, it is predicted that we'll be using 2 by 10 to the 20 bytes per month, which is 200 exabytes. This is roughly 13 times bigger than the total amount of data held by Google. So it's very important, needless to say, to keep looking into ways to improve the situation, to make data transfer more and more efficient and faster. So generally, we would use photonic circuits over electronic circuits for these applications because they're faster, they don't consume as much power, and most important, they offer a greater bandwidth, which simply means that more data can be transferred from one point to another within a specific amount of time. So this leads us on to the next question that should be asked. What exactly is a photonic integrated circuit? So it's basically the optical equivalent of an electronic circuit. So instead of having components such as transistors and resistors, instead you have lasers which produce the light, waveguides which guide the light from the laser throughout the circuit, filters which can be used to select the wavelength that is outputted, photodetectors to detect the light, modulators which can change the phase and amplitude of the light, and power splitters because sometimes you need to separate light into multiple channels. So a highly functioning PIC would contain most or all of these components. So this figure here to the right is an example of what a PIC could look like. So you have your laser, your modulator, your waveguide, you've got couplers, and you also have an optical ring resonator, which is the filter function of this PIC. So this would be considered a multifunction PIC. So what are the PICs made out of? So the answer to this is generally silicon. Now, you don't have to have your PIC made out of silicon. There has been PICs that have used other platforms and materials such as lithium niobate, 3-nitro materials and polymers. But silicon is definitely the most common materials for PICs, and there are good reasons for this. So it's compatible with CMOS technology, which is the same technology that is used to develop microprocessors and digital logic circuits. So because of this compatibility, there's a high volume of production when manufacturing silicon PICs. If we also look at the optical properties of silicon, silicon is a very good waveguide material. And this is due to the high index contrast between silicon and silicon oxide. So silicon would generally be the waveguide core, and then silicon oxide would be the top and bottom cladding. Although you could also have a really high index contrast between silicon and air, for example, because air has a refractive index of 1. But because of this high index contrast, and you can see this over here, the silicon is tightly confined to the waveguide. So there's less and less of a chance that it's going to leak out. So silicon also has really small dimensions. For example, if you want to design a silicon waveguide that only supports fundamental mode, the height of it would be about 220 nanometers, and it would be about 400 or 500 nanometers wide. So you'll have very compact silicon devices. So because of the small footprint and the CMOS compatibility, silicon is a low-cost material, and it's also highly abundant. It is, in fact, the second most abundant material on the Earth after oxygen. So silicon sounds like the perfect material for a photonic integrated circuit, and ideally you would have every optical component on the circuit made out of silicon, but you actually can't. So there are disadvantages to silicon. So it is very inefficient for producing light, and this is due to its indirect band gap. So if we have a look at the diagram over here, we can see that 3,5 semiconductor materials such as indium phosphide and gallium arsenide have a direct band gap. So for radiative recombination to occur, only a photon is emitted. But for silicon, because there's an indirect band gap, in order for radiative recombination to occur, a phonon, which is a vibration particle, has to be emitted or absorbed for the photon to be produced. And this is due to conservation of momentum laws. So the involvement of the phonon makes the process of radiative recombination much slower and less likely to occur. So therefore, rather than using silicon as a laser, we would instead use 3,5 materials. Silicon is also centrosymmetric. So as a result of this, it lacks or has a very weak electro-optic coefficient. So this means that it wouldn't be used for fabricating modulators. And while silicon is transparent in the telecommunication wavelength range of 1.3 to 1.6 microns, it doesn't actually detect in that range. So you also couldn't use silicon for a photodetector. So this is where photonic integration is really important. In order to have a multifunctioning PIC while exploiting the advantages of silicon, it's important that we're able to integrate different materials with the silicon photonic circuit. There are three headings that photonic integration methods fall under: monolithic integration, heterogeneous integration, and hybrid integration. In the following slides, I will be outlining these headings and the examples of these methods that are currently used in fabricating PICs. Monolithic integration is the direct epitaxial growth of material onto the silicon wafer. So the optical functions of the circuit would be made from silicon and one additional material. The material could be used for one additional device, or it could be used for many different optical devices. So there's an example over here where they've used erbium material for the DFB laser source and for the fiber chip coupler. And then the rest of the circuit is made from silicon. So this is actually a low cost technique compared to the other methods. But the main issue with monolithic integration or with any kind of epitaxial growth is the lattice mismatch between the materials. So it's kind of like squeezing or fitting two boxes together that are of different sizes. Stresses and strains are induced, which can cause defects to occur, which can then compromise the performance of the devices. Heterogeneous integration, therefore, would be preferred for a multifunction PIC. So multiple materials are incorporated into the silicon PIC, allowing for a more compact device. So there are two main methods of heterogeneous integration: wafer bonding and microtransfer printing. So you would have learned about microtransfer printing on Tuesday with Emma. So to the left, here's just a schematic of transfer printing a DFB laser. So the PDMS stamp head comes down, picks up the laser coupon, and then places it on the target substrate. To the right here then is an example of die to wafer bonding. So dies are the pieces of the wafer, and each die contains multiple picks. So wafer bonding can be through die to wafer bonding or wafer to wafer bonding. So wafer bonding is essentially fusing two wafers or dies to wafer by applying high temperatures and or pressure. So there's many different ways of wafer bonding. So anodic bonding here is when the two wafers are heated and an electric field is applied. To the right here and in the previous slides, both of these are examples of adhesive bonding. So adhesive bonding is when there's an intermediate layer used for the bonding. Generally, the choice of this material for this layer depends on the substrate material and the topography. So polymers are commonly used, with DBS-BCB being a popular choice as it doesn't create unwanted byproducts when it's cured. So the advantages of adhesive wafer bonding are that it's low temperature processing and the surface planarization, so you have a smooth surface after bonding. There are advantages and disadvantages to wafer bonding. So if you remember from your micro transfer printing lecture, alignment is a very key thing in transfer printing. You don't want to misalign your devices to waveguides that you're coupling to. So there's tolerances there. But with wafer bonding, you don't need to be nearly as accurate with the alignment. There's a high throughput and there's a low cost to wafer bonding. And because you're putting all the material onto the wafer, you can have dense integration of devices because you can etch away and form however many devices that you want on the PIC. And there's a reduced packaging cost. But the main disadvantage then is that there's differences in thermal expansion over large areas. So this can make it difficult to bond two wafers. So you can end up with thermal stresses being induced. As I was saying before, you etch away the majority of the wafer. So, while that's good in terms of, you're free to form how many devices that you want, you're actually being really wasteful then of the material that's being etched away. And if you're using something like indium phosphide, for example, which is a material that's running out or not as abundant as silicon, that's really, you're wasting a lot of that material. And another thing with wafer bonding, again, going back to microtransfer printing, you can test the devices, but because they're unfinished when it comes to wafer bonding, you can't. So you don't know if they're going to work until they are transferred to the silicon and finished off. So there's no reliability there. So hybrid integration is the third heading of photonic integration. And this is the integration of a finished gain chip with a silicon photonics chip. And this is usually done through flip chip bonding. So you can see here to the left that there's an array of in-gas lasers on this chip. And it's going to be aligned up and flip chip bonded with this silicon chip that contains an array of tapered waveguides. Now, the chip that is to be flip chip bonded doesn't necessarily have to be the gain chip. Over here, we have an example of a tapered waveguide that's going to be coupling to a polymer waveguide. But the key thing is that these chips have finished devices on them. So your gain chip, or the chip with the photonic devices that you want to transfer, is flipped and it's bonded onto the silicon photonics chip. So the connection between this gain chip and silicon photonics chip is made by using an array of bond pads and connective bumps that are usually solder or adhesive bumps, but can also be stud bumps. So the gain chip is aligned to the silicon photonics chip, and then by being heated and compressed, the bonds are formed between the chips. And then to reduce thermal stresses occurring, an underfill is dispensed between the gain chip and the silicon photonics chip. And this underfill is a polymer material. So there's advantages and disadvantages to flip chip bonding. So again, just like with micro transfer printing, flip chip bonding requires a high alignment accuracy. So, if you misalign in any way, this could affect the performance of your overall PIC. So just like microtransfer printing, you generally require alignment marks to make sure that the chip is correctly aligned with your silicon chip. And as a result of the alignment limitations, it can be difficult therefore to scale up and reduce the cost of the PICs. Also, unlike wafer bonding, where you can etch away the material and form as many devices as needed, you can only integrate so much with flip chip bonding as it depends upon the pitch and the size of the bumps. However, unlike wafer bonding and like micro transfer printing, you know whether or not a device is working as the devices are finished on the gain chip. So yeah, there's reliability. You know that, okay, I'm flip chip bonding this device to this circuit. I know it already works. I've already characterized it. So the main issues that will arise after that then will be to do with the flip chip bonding, if there is any. So the main summary is that each photonic integration method has its advantages and its disadvantages. So it really depends on what PIC you're designing. Some would be suited more to others. You could get away with just monolithic integration. Sometimes you might need transfer printing, wafer bonding. So it really depends on the design of your PIC. But regardless, it's important to use a method that will allow for low cost fabrication, scalability, and high volume production without compromising the efficiency of the device, so that when you've integrated all the devices and you've got your fully formed PIC, it's working exactly as you expected it to. So thank you for listening to my talk. I hope you found it a bit interesting. And if you have any questions, you can ask away.